Okay, welcome to class and shush. Welcome to class. And what we're going to do is we're going to quickly go over particulate diagram interpretations. That's where we left off. We talked about IMFs, 3 types, London dispersion, everybody has, dipole, a level up, and with polar molecules. And then H bonding. Hydrogen likes to FON, phone a friend, okay, as the strongest IMF. And then we have this weird interlude of an IMF, which is ion dipole that is specific to ionic compounds in water, aqueous solution. All right. And then we talked about how might we show these things? How do we draw illustrations through particulate diagrams? And what you have here is, this was an actual AP old question. We have a, describe the contents of the container below. So what did you say? Yes, Sky.
It was an impure homogeneous.
Impure homogeneous mixture. Okay, it was a gas. Particularly, it was impure. How many components were in it? Yeah, like how many? No, more just like what's the mixture made of? 2, 3 things, 4 things? 2 diatomic compounds. What else could you figure out about those diatomic compounds? Huh? What else? There's one more thing you could figure out from this picture. 2 more things, actually, you can figure out from this picture. Yes, you have a 6:3 ratio or a 2:1 ratio. What else can you figure out? Look real closely. Yes. Yes, one compound is larger than the other. So we have one that's larger than the other. Okay, size. Okay, excellent. So a lot of the problems with you drawing particulate diagrams, which by the way is a really common FRQ, right, Charlie? It's a common FRQ to draw those. Charlie. So we have one larger one. The ratio is really important and the size is important. So one thing that you want to keep in mind when you're reading and drawing diagrams is making sure that you never make a mistake in terms of, oh, it just happened to be like that. No, nothing just happens to be like that in a particulate diagram. Everything means something. Okay. FYI, I'm not a Blenders fan. So for Teacher Appreciation Week, don't give me Blenders gift card. I get too many of them and I always give them away to students. So don't get them for me. Yes. I have no idea. I think sometime May, like close to Mother's Day. Because like low-key teachers are like little mini mothers, right? Right? I mean, huh? The close to Father's Day, just kidding. Okay. So in sample, the sample in part A is cool to the point that the contents of your container are now in the liquid phase. Using the empty space, I don't know, man, draw a box.
That'd be so awesome.
Huh?
Maybe not for that kid.
What?
I said that Chad has kids.
Oh man, I hope my kids think one day I'm cool. I don't think so though. I think they'll be like, stop. And I'll be like, love me. Use the empty space above to draw what you believe the contents of the container will appear. Clearly describe the nature of your drawing so it addresses. So I really don't feel like going over this, but what were some of the features that were part of your drawing for liquid? What was the main changes that you had?
The atoms are closer together.
Yeah.
The compounds.
The compounds are closer together. Honestly, that's kind of the big difference right there. That's like the big difference. You're showing a liquid closer together than the gas. I would have also kept the same amount of each compound, right? Because you didn't see anything disappear. All it was that changed was the state of matter, not the actual number of particles. So you wouldn't want to change any of that. You wouldn't want to change the shading. You wouldn't want to technically change the size comparison, right? Only thing that you really wanted to change was the closeness. Oh, who was that? Okay, good. It's not Hernandez. Okay. So, okay. Example 2. The diagram below represents H2 and N2 in a closed container. Which of the following diagrams to the right would represent the results if the reaction was shown below to proceed as the following? For every 1 N2 diatomic, we have 3 H2 diatomics reacting to produce 2 ammonia. This is a really good compound to know. It's ammonia. It's very commonly just part of problems on the AP exam. So it's just really good to know. It's like ammonium, but one less hydrogen, so therefore uncharged. Okay. So what did you guys say? Oh man, I never got to finish my lunch. What did you guys say for this one? If we have so far, we start with 3 N2s. We start with 3 H2s. So what is the maximum possible NH3s you can get? Well, for every 3 N2s, we're going to get 6 NH3s. And for every 3 H2s, we're going to get 2 NH3s. So which one is going to limit us? Hydrogen is going to limit us. This right here is going to be what we call the limiting reagent. It's, in terms of reaction, it's going to be the one that runs out first. So as a result, how many N2s are we going to be left with? For every 3 H2s that react, we need what? How many N2s? We need 1 N2. So how many excess N2s are we going to have? 2 excess N2s. So your diagram should have something that has 2 NH3s and excess 2 N2s. Which one was that? Which one? B. B. Excellent. No. Look at it closely. What's in the middle for B? What's the center molecule? What about E? I think it is E. Because you have 2 NH3s. Remember, the dark ones are 3, the H's, and you have 2. Did you say E or B? I heard B. Oh, you were saying E. Say E for excellent or elephant. Guys, help me. Okay. So, good. This is just a great interpretation practice, and we're gonna move on. So, somebody tell me KMT theory. What are the 2 main postulates? Postulates or principles of the KMT theory, kinetic molecular theory.
Gases have no attractive or repulsive forces.
Gases have no attractive or repulsive forces. What else, Jay?
Collisions are elastic.
Collisions are elastic. So when you collide into each other, no energy is transferred, no energy is lost. You are still continuing in straight line vector motion. Parikh, what else?
Collision has an effect on the motion of the.
Excellent. Temperature is directly proportional to the motion of the molecules, which by the way makes sense because temperature is technically a measure of kinetic energy. What else, Sagarika?
Any nature of a molecule's matter is negligible compared to the distance between the gas particles.
Yeah, so the volume of the particle itself is negligible compared to the volume between or space between the molecules. Hayden.
Well, this doesn't necessarily only apply to gas. The particles are always in motion.
Yes, particles are always in motion. By the way, I think I introduced early on why we have Kelvin, a unit Kelvin called temperature. Kelvin's the only unit of measurement for kinetic energy where you truly have 0 kinetic energy. 0, like no motion of particles. All right. But otherwise, everything else is like all your solids vibrate. We say that they vibrate. They obviously don't move in vector line motion. They just vibrate. Good. What does the Maxwell-Boltzmann distribution tell us? Emin.
Well, I guess at a given temperature, all gases have the same quote unquote average kinetic energy. So the area under the curve is going to be the same.
Wait, what?
That's what the Maxwell-Boltzmann distribution tells us.
Oh, yes.
Are you not asking about that?
No, you're just slightly wrong, but that's okay. So you are right in the sense that it does show us kinetic energy, and the space below it would be the average kinetic energy value. But what it particularly shows us is the percent of individual gas molecules that are moving at a either higher or lower than the average. How we get the average. It's like the isotopes of movement. Okay. It's like, well, this percentage of the molecules out of that whole sample are actually moving a little faster than the average. And what is happening in front of me right now? Hocus pocus. Okay. So there's also this particular special area. We're going to address that later when we talk about Unit 4 reactions, and I believe Charlie will be introducing that. Excellent. So you were right, but you were just also wrong. You were right and wrong. So Maxwell-Boltzmann distribution is particularly important, and it's a common like MCQ interpretation to illustrate a couple things. All else being constant, if you were to change the temperature, you shift the curve right or left for the same gas sample. All else being constant in terms of temperature, if you have two different gas samples, you can shift left or right depending on the size of the molecule and the relative speed it's going at. Because remember, velocity times mass is, well, squared, times a half is kinetic energy. So you can find out two separate pieces of information depending on the conditions that you're setting up the graph, okay? And then of course I introduce, well, the KMT is basically the outline for what an ideal gas behaves like. And now we're moving into that second subtopic that I told you guys was weird about gases, where you have this like IMFs and then gases and then solutions, like where unit 3 is just like almost 3 mini units in itself, okay? So we're moving on to gases. I told you about the conditions, and now we're going to talk about gas and pressure. So I'm just going to introduce some of this, and then Kevin's going to come up and explain. I think he explained it better when the first time he ever taught in front of the class, he actually did this problem, and he explained it really well, better than I did because of his physics background. So I'm just going to introduce some of the instrumentation of how we measure gas pressure that's created from these ideal gases that are in straight line motion that collide with surfaces if stopped in a container. And then he'll explain the problem, and then we'll move on with our life. So gases, moving on. Gases, as we know, if they're behaving in ideal conditions, which is, by the way, high temperature and low pressure, and we're assuming that they behave ideally, no IMFs, negligible volume, and so forth, straight line vector motion, we can measure them with certain materials. And by the way, you don't have to be an ideal gas to measure this way. It just kind of goes with how do we even know this is happening? Okay, gases, as we know, exert a pressure. How do you think we blow up balloons, right? Gases exert a pressure. And one thing that we do is we measure two types of pressures. Okay, we call atmospheric pressure as one type of common gas pressure that we measure. The atmospheric gas, right? Atmospheric pressure. And of course, this is the force exerted by air. And don't forget, air is a gas mixture. So when you leave your like water bottle open, there is a pressure that enters into your water bottle, and it keeps more of your volatile molecules from evaporating. It keeps them down. It slows down the process. Okay, yes.
This is a stupid question, but does that have anything to do with like the force of gravity?
Oh, physics people, does that have anything to do with the force of gravity?
Pretty sure the weight of the air is what's causing
But it has weight because of gravity.
Yeah. Honestly, this seems above my pay grade. So I don't think it's essential, but that's an interesting question. No one's asked that. For the record, for future classes, does the atmospheric pressure have anything to do with the actual gravity? Would it be different on a different planet? I want to say yes, but I can't back it up. Right, sure. Yeah, I've never been to another planet. I don't know.
Like atmospheric pressure on the moon is not the same.
Yeah. See, there we go. I don't know physics. I don't know. Okay. Yes. Fareed?
You said that that's just sort of like a collision of atoms in a contained space. So
Yeah.
why would gravity have to do anything with that?
Well, we measure it in a contained space. Yeah. I mean, technically, like, it's colliding at something, right? It's a relative.
On a different planet, it's a combination of the mass of the planet and the makeup of its atoms.
This is really physicsy, and I would like to move on. I am going to move on. This is out of my field, okay? I'm just going to put it up there. There is, by the way, when we hit the last unit of AP Chem, I like hands off from me. I do not enjoy that unit. I let other people teach that unit. It is too physicsy. No, it's electrochemistry. That is not my thing. So anyway, we measure through a what we call a barometer. That's like old school, but we do it. Barometer uses liquid mercury. Mercury is, I think, the only metal that's naturally liquid state at room temperature, and it's super heavy. It's so cool, and it sloshes like all epically. Okay. It never like fully separates you when it sloshes. It's just like whoosh, and then it comes back down. It's so cool. So and look, man, a little bit of poison never kills
We
it.
all breathe hydrogen.
So anyway, we say that 760 millimeters of mercury is known as standard atmospheric pressure. Okay, so the second way that we can kind of quantify gas pressure and the way that we look at it, okay, is more particularly in a closed container. Because technically atmospheric pressure is you have to like consider it, you have to create your own bounds and say, well, this is like my closed container for atmospheric pressure is whatever it's hitting. Maybe it's not actually closed, it's just the comparison of the force, right? But here we actually do look at it in closed container and we say that this is actually called gas pressure. It's just a nuanced terminology, atmospheric versus gas. But if we say gas pressure, we usually assume that you're talking about in a closed container. And this is measured through a manometer. Okay, and even I put a note to myself, Kevin explain. So, Kevin. So come here. You'll be in the video.
Wait,
Look,
Judy, you give, by the way, Kevin, the part that we couldn't figure out how to explain.
he figured it out. Yeah, we talked about it. So here's the manometer, and Kevin's gonna explain how we derive the equation, and then you're gonna do the practice problem. Okay, so Kevin, sit. I'm gonna eat my spring roll.
That actually looks so good.
You
From
just
Whole
mean
Foods.
like this, right? The plus and the minus?
Well, yeah, but then this is the equation. So just explain how the manometer works. You got this. So if we're trying to figure out the pressure of the gas, this manometer is a U shape too. Okay, we literally talked about this. What are you doing?
What does
Um,
it say?
What do you mean? Due to the
Dive?
height, due to the height change.
Do.
Okay. So this is a U-shaped container. I think it's cute. I think it's real cute. And what you have is you have some gas sample. Okay, you see that little knob at the bottom? If we wanted, this is by the way how we release gas in fancier hoods. We have to keep a consistent gas pressure, and we often flood our reactions with like a specific gas, like nitrogen or argon, which is non-reactive, to take up the space in the container, so it doesn't like implode or react with byproducts. And so what we do is what we have is a valve, and that manometer valve will measure if you're going really old school. More modern things have barometers, which is ironic because it's a closed container. But anyway, and what we do is we turn that little nozzle on it and release the gas into the flask. Okay, and the way that it measures it is through this manometer, which has some set amount of liquid in it. And now Kevin's going to tell you how we would determine the gas pressure for that sample based on how the manometer liquid moves.
So if we look at like the regular where they're both level, right? This means that the pressures on either side are equal. And so obviously, if once they go to not equal, the side that has more pressure is going to push down more on the liquid. So that side's going to be lower. So like in this one, how this side's lower, that means the atmospheric pressure is greater than what's inside, which also means that like this is less. And so which is why we have to subtract the height, because it will be less anyways. And basically the same thing for the opposite. And then I think you'll get it better if we're doing the example first. So when a container of gas is connected to the manometer, the mercury in the open end of the U-tube rises until it is 112 millimeters higher than mercury in the container side. If the atmospheric pressure is 765 millimeters, Hg, what is the gas pressure in the container? So yeah, let's start with this level, right? If it's level, then we start with the equation where the gas is equivalent to the atmospheric. And then it tells us that the open end is 112 millimeters higher. And so that's like this one right here, right? So if the open end is higher, that means that the gas inside has a lower pressure. So that means you have to add the change in height, right? Because if we subtract it, then it'd be smaller, and that's not right. So we have everyone knows what delta is, right? Yeah, okay. And then we just plug in our numbers. Yeah. And okay, and then the equation here that's supposed to go here is just PATM. Pressure atmospheric plus pressure due to change in H. And next, I think you have some practice conversions, so I guess you can start doing that while we switch over. You don't have to switch?
Can you go up a little bit?
Yes. So I don't need me to explain how we got.
Do you only measure things in terms of atmospheric pressure? Does that make sense? Like use it as like the standard.
Most commonly, we use atmospheric.
So the units for the 877 is that atmospheres or pascals?
No, that's whatever this is, whatever this is. Yeah.
I don't think that's a unit of pressure.
Yeah.
No, it is. It is. I just don't know what it is. Yeah. I don't know. I've never seen it before either. So.
Psi? Psi?
No, the HG.
Hg, mercury.
So you measure pressure.
Millimeters of mercury. Hg is the chemical symbol for mercury.
Wait, you
Oh.
measure pressure with mercury?
So you measure pressure.
That's the liquid mercury in the barometer.
Well, yeah, but like you measure pressure in millimeters of mercury.
Because it's how much it moves up the little thing.
Also, I said, and gravity does affect.
What do they do?
Atmospheric pressure.
Cool. Yes.
But like, can you just make a barometer with a jar and just
Look, man, this is what the textbook told me to teach you. Okay, give me a break.
Water.
Sure. Sure. We could do it with a lot of things, folks. Okay. We could do it with a lot of things. Okay. So, wow, that handwriting. Can you guys all read that? All right. Fair enough. Fair enough. Okay. Thank you, Kevin. Let's all clap for Kevin. Okay. So, let's move on to vapor pressure. How is vapor pressure different than gas pressure? Yes.
Okay, in the barometer and stuff, is the amount of mercury like standardized? Because if you have, okay, then the tubes are also the same size. Because if you
Sure, man. Sure. That would make sense.
Can we make one? A lot bigger, but the same. Can we make one as an experiment?
You know what? Yes, Charlie. Save me.
The reality is that if you make the tube wider, you're increasing the surface area and the pressure acts proportionally more as well.
Exactly, so that's why I asked, the tube is standardized as well.
I don't think it has to be, because if you change the size of the tube, you're changing the weight of the mercury, but you're also changing the surface area that
If
the
you
pressure is
make the
acting on.
tube wider, but you keep the same amount of mercury, then you have more pressure acting on less. on the same amount of
Maybe,
mass.
yeah. Pressure. Yeah, I don't know.
Is there? No, Dalton's law. Dalton's law. Yeah.
Still mercury like on both sides. It doesn't-
Good luck at tennis. Okay, so anyway, here's my thing. I think Kevin said this, but I would highlight that we use these two. Okay, atmospheric is more special in chemistry, but we can do millimeters of mercury in an older FRQ if they decide to pull one up from the banks. Okay, torr, kilopascal, psi, and bar are all way more physics-based. We do not tend to take those on. All right. So what about vapor pressure? Vapor pressure is different than gas pressure because vapor pressure is the pressure exerted by any substance due to, okay, due to the, hold on, vapor portion above the liquid portion of a sample. So technically, vapor is a gas, but we have this subcategory name for it because vapor is the volatile molecules of a liquid sample that have evaporated into the gas state, but the sample itself is not gas. The sample is liquid with some gas particles that have just gained enough energy to enter the gas phase on top of a liquid. Okay, so vapor is not treated the same as necessarily gas sample. It's just liquid particles that have happened to gain enough energy to escape into the gas phase. Yes.
Why do certain molecules end up energy?
Because it's about access to the energy around surrounding environment. So it's heat transfer. And they're the first to be exposed to it. So that's kind of the main idea there. And I don't really know why this is all crazy out of order. Yeah, so remember, particles don't absorb evenly. Like in a gas sample, they don't. So the vapor pressure as a result, because it's just a result of a liquid, some of those particles, depends on the chemical structure. Okay, and second, it depends on the temperature, of course, of the substance. So the higher temperature environment you have, the more likely you're gonna have a higher vapor pressure, because the more of those particles that are gonna be able on the surface of the liquid to escape. Okay, there is a maximum vapor pressure that exists for every substance, just FYI. And boiling is really defined as when the substance's vapor pressure reaches atmospheric pressure. So you get enough molecules from the liquid to transition to the gas phase to create enough pressure to equalize with the atmosphere's pressure. That's actually boiling. So if an atmospheric pressure decreases, by the way, what you see is that you will boil at a lower temperature. So in Colorado, we boil quicker because we have lower atmospheric pressure. We have thin air. Okay, so bakers, when they transition states, especially states with different altitudes, they have to bake differently. That's why you see why baking is actually considered a very fine art. Yes.
So what if I'm like backpacking at 10,000 feet and then it takes longer to boil water? Why is that?
Because it's colder.
No, it's the same temperature and it takes longer to boil the water.
Yeah, wait, I feel like that question has multiple questions before we can answer that. So we're gonna move on. The greater the IMFs, this is a tie-in. Greater IMFs, obviously, we already know this connection, higher boiling point. Okay, so there's two reasons why you might see a variance in boiling, according to the definition of what boiling is. Okay, so when we think about quantifying gas pressure, okay, and we could do vapor pressure, but let's just think about gas pressure in general. We have a unique law called Dalton's law of partial pressures. And that tells us in a mixture of gases, such as air, right? Such as air, atmospheric pressure, and a mixture of gases, the total pressure, okay, the total pressure of the system, whatever your system is, whatever you decide you're analyzing of the system, okay, equals the pressure of each individual, which is like kind of like a no-dirt, equals of each individual gas combined. Sounds silly, but the math is actually really valuable because what this tells us is that we can quantify the individual contribution of each gas, which means, by the way, if we know the total pressure and we know most of the individual contributions of the gas, we can figure out an unknown gas's contribution and therefore the amount that is present. So it's actually way more helpful than you think it is. Yes.
Does it boil at lower temperature?
Yeah. Sheesh. Thank you. Sorry. Thank you. Sometimes I speak things into writing that shouldn't have been spoken into writing. Okay. Boil at lower temperatures. Okay. So here's like a little picture. Obviously, okay, gas A and its partial pressure added to gas B and its partial pressure added to gas C and its partial pressure. If you combine the total thing, okay, you get this equation telling me that that's the total amount of gas. Okay, sounds insane, but somebody got famous for that, named Dalton. Okay, he did 1 + 2 + 3, but with gases. And that is, sir, is how you get remembered in the books forever. Okay, so let us not forget that, and you were a male back then. You were a male. You were a white male. Yes. Because you didn't really need to understand partial pressure to answer that question. It would have been helpful, but you didn't need it because it's more about mass. Did you have a question or are you just stretching? Okay, so the percent mole contribution of one gas is what we call the mole fraction. So remember, if we're talking about particles, we can quantify them in the mole, right? So we don't have to just stick to how much pressure, because on the end, that might not help us. Maybe we just need the individual pressure contribution to figure out how many particles are present. And if we know the particles present, okay, that tells us the overall mole ratio present between those individual components. Yes.
I guess this is kind of tangentially related, but why don't gases separate out into their own individual? Like, why is it a homogeneous mixture when they vary?
They can separate, but we don't see it. And generally, the speed at which they're moving at, they're all in the same environment. So you have the straight line vector motion just colliding through. And very rarely is density that significant because you're really looking at really lightweight things overall. So the density difference also doesn't offer that much of a separation. But yes, you can technically separate. So the equation for this would become that the partial pressure of one specific mixture in the compound is equal to the mole percentage of the moles available of that compound times the overall pressure. We simplify this into mole fraction. That beautiful X shape sub A is the symbol for mole fraction. So it's a way for us to get to what we really care about, which is not the individual pressure itself, but the mole presence, the mole fraction present, the percent of moles of that gas present in that partial pressure sample, okay? And so what we get is that the simplified way is that N of whatever compound you're looking at, the moles of A over the total moles times the total pressure. And that equation right there, super simple, super basic, super helpful actually, because what we can do is we can solve for pressure and we can solve for moles. That's a nice breakdown from the simple 1 + 2 + 3 method. Okay, it gives you us more valuable information as chemists. Yes.
Do gases with the same mass have the same pressure?
Theoretically, yes, if they're moving at the same velocity and in the same environment. Yes. So here's a quick problem. Go ahead and try out this problem. It is way easier than you think. So for this problem, it should have been real nice and easy. You know that the total pressure, okay, is 2 atm. All right. Oh, you probably need a little bit more time, don't you? No, not too bad. Okay. So you know that the total pressure is 2 atm. Okay, that equals P tote. P tote. Okay. And you're asked to find the individual partial pressures of each, recognizing that you're given the mole values. So you know that your total moles, N tote, is equal to 7.35 moles. And then you have each individual, N, NE. 4.46, sorry, I'm like misreading, 4.46. You know that NAR is 0.74. You know that NXE is 2.15. So what you had to do was to find out the partial pressure, guys, of NE, you would do the mole fraction of NE times the total pressure. So you get that, okay, 4.46 all over 7.35 moles times partial pressure ATM. And you should have gotten, apparently Maggie got it right because she's crying over there, 1.2 ATM. Maggie, by the way, did try to quit and she couldn't. Her counselor told her no. Just so you know, she's here against her free will. Okay. The next one is argon, right? You said that's the same setup. Partial pressure mole fraction. Okay. All over the total mole yeah, moles present is 7.35 times partial, total pressure to find the partial pressure, and you'd get that P argon is equal to 0.20 ATM. Okay, and then finally for xenon, anyone watch Xenon Girl? Anyone watch that? That was like, came out when I was in like 3rd grade. No, okay, it's totally fine. Parents in the background, I'm sure you know, have heard about it. So, how old are your parents, by the way? Are they near my age? They're twice the age? I'm 25.
Not twice, but.
Yeah. What are your parents like, 40s? 50s?
Well, it depends if you're the first or second.
50. Okay, so I'm not there yet. Okay, P XE, okay, partial pressure of xenon is gonna be 2.15, again, all over the total, 7.35 times 2, and you get, Maggie, okay, you get 0.80, and as a safe check, it theoretically should add up to, what did I do wrong?
Is it 0.585?
Is it, I don't know, I'm looking at my old notes, but I think we got that one wrong.
0.80, that's something.
I think
Yeah,
it's
0. What'd you guys get?
0.58.
5.
59 if you round up.
Okay, let's do 5.8 because we rounded weird on the other one. Sorry, guys. I think I remember someone correcting me later and I printed off the old copy of the notes. So, okay, like I said, easy check. It should add up to 2. It should add up to 2. All right. So all of that is kind of side pieces to the main course, which is we summarize pressure, volume, temperature, and amount of moles for a gas in one solid equation known as the ideal gas law equation. And notice this ideal gas law equation is assuming ideal gas behavior. That's how we derive the equation, is assuming that. So the ideal gas law is the following. It's called Pervner. Okay, P V equals nRT. Pervner. Okay, last year I said it wrong. That was embarrassing. Pervner. Okay. Sky, you know what I thought. So what we have here is, okay, we have pressure times the volume of your gas sample is going to be equal to moles times what we call the R constant times the temperature it's at. And this is how we move on from doing little mini calculations and quantifications and descriptions of gas to one big equation that kind of hits up all the areas that we can explore with gases. Amount, temp, which is really kinetic energy measurement, volume, the space that it takes up, and the pressure that it exerts within that volume. Yes.
I assume R is on the equation sheet?
Yes, so R is on the equation sheet. You have 2 main constants for R on the equation sheet. What you need to remember is that the units for R must be the same as the units for your other variables. That will tell you what R you should be in. Because obviously the idea is that your constant, any constant that you have that's in an equation is relating all of your variables, which means it has to have the correct conversions, respective conversion between those units, which means any constant has to have all of those units that your other variables are in the same, or else you're using an inaccurate comparison between them all. All right. So our favorite one is this R value. It is provided on the AP equation sheet. All right. There's another one called 8.314 or 0.8314 that can sometimes be used. You'll know because you'll notice the units are different. Okay. I'm going to highlight a couple. So we've got this one is a common one, 0.0821 liters times atmospheres all over mole times Kelvin. Okay. Then another one is what we call, let's do this one, 8.314 joules per Kelvin. Oh, joules, okay, per Kelvin times mole. That's another common one. Those are your 2 most common. And something that you should also know about this equation is that temperature has to always be in Kelvin. So whenever you work with a gas, you have to measure everything in kelvins for temperature. You calculating in degrees Celsius won't fly here. It has to be in Kelvin. So remember, degrees Celsius plus 273.15 equals Kelvin is going to be your conversion that you always do. In other math problems, you can keep it in degrees Celsius. In ideal gas law problems, you have to change it to Kelvin. The numbers will not work. Okay. So go ahead and try out your practice problem using your Pervner ideal gas law equation. So this was a really nice one. With ideal gas law problems, it's usually really nice because it's usually a plug and chug thing. You have the equation, maybe you need to convert the individual variables to the right unit, but then you pretty much have all the information you need except for one variable and you solve. It's usually really nice problems. Like you kind of hope and pray that you get an ideal gas law problem because it's basically like, hey, I know pressure. No, I want pressure. Okay. And I know moles. I know degrees. And remember, I have to change to Kelvin. So maybe I have to do a little conversion beforehand. And I know volume. And I know my constant based off of the units I'm in. So what it becomes is just like, hey, solve for the unknown. So we do PV equals nRT. And we just rearrange to solve for pressure. So nRT all over V. And when you plug in those values, it becomes what? 1.82 moles. Okay, times 0.08206 liters atmospheres all over moles Kelvin. Okay, times 342.6. Sometimes they round it differently, depending. Do whatever the AP equation gives you, sheet. Whatever AP equation sheet gives you. Kelvin. All over 5, Maggie. 5.43 liters. And you get that the pressure in ATM, because you'd cancel out every single unit except for ATM, you'd get that it was 9.43 ATM. Okay, so it's really nice. It's really nice. Now, what if you just want to compare two variables at a time? What if you see, hey, I don't want to look at this statically, because by the way, this is an equation that's applied at static, in a static situation in terms of these are set. This is like right now, this is happening. This is the only conditions we're in. Okay. But what if you change conditions, right? You increase the temperature, you decrease the temperature. We have individual sub-gas laws that help us address dynamic changes, okay, in gas conditions. But first, Nora.
Is that the appropriate amount of work to show for yourself?
Yes. Yes, it is. Yes, it is.
If you don't put units, would they take off points? Like assuming you went.
Sometimes they do. It depends on the FRQ.
But if your like answer has the right unit, would they care if your work has seen? Assuming you like understood what you were.
Sometimes it kind of there's a couple where they specifically ask you to only set up the problem and not solve it. They just set it up. That's when you definitely want it. So my feeling is like if there's a questionable, so one thing that's common FRQ question that you gain a partial point for in a problem is sometimes in like a multi-series dimensional analysis, they look for your unit conversion between moles. And if you don't have the word moles, it's hard to identify as a grader. So they might run over it and not give you the point. So usually when it comes to like mole ratio stuff and switching between substances, that's always a good unit conversion to include the units on. And then of course your final answer. Yeah. Okay. So we apply this ideal gas law equation for non-ideal gases. We apply this ideal gas law equation for non-ideal gases as well, because real gases also demonstrate pretty similar relationship. We might see a slight overestimate or a slight underestimate when we actually measure in lab, but we would get really close, and the relationship in terms of indirect versus direct is consistent between the variables. So let's talk about what if we change a condition. So here we have these individual gas laws, and these gas laws all of these gas laws address initial versus final or dynamic conditions where you're changing something. Okay. So whatever variable you decide to change, you have to assume all other variables are equal or fixed so that you can just look at two variables affecting one another. I change one, it's going to produce this exact effect. So we say that Boyle's law is the relationship between pressure and volume, and pressure and volume have a indirect relationship. So what we do is we take the ideal gas law and we say, what if we were to set this equal to one another? Condition one ideal gas law, PV, okay, all over, let's do this. Let's set it up this way. PV all over nRT1 is equal to pressure 2 over volume 2 all over N2 all over R, which is not a 2, it's just the same R, all over T2. What we would see is that if we were to create an initial versus final equation, that if we assume that I change volume and everything else stays constant, it's like all of these become a constant 1. So what we get is this relationship that P1 equals V times V1 equals P2 times V2. We get this relationship that the initial conditions between pressure and volume are equal to the final conditions of pressure and volume multiplied by one another. So we get P1 V1 equals P2 V2. And that's what we call Boyle's law. That's when we isolate pressure and volume, fix everything else, and we just examine shifts in one of those two. And it should show an indirect, right? The less volume you have, the more pressure because you're squishing the gas molecules down. Yes.
What does it say above address?
Initial versus final. Okay. So is Kevin's handwriting really that much better than mine? I don't really feel like that. Okay, that makes me feel better. Okay, so we would do, okay. We would do, Charlie, there's a law named after you. We do Charles' law next. Charles' law is the relationship between volume and temp. Of course, we know that volume and temp are gonna have a direct relationship, right? And that makes sense, by the way. The more I increase gas molecules, right, the more space they take up, which is why a hot air balloon works. Why you heat up the gas molecules in a hot air balloon, they expand the area, okay? You also know this if you leave something really hot in your car, right, a water bottle, and it can implode, or a can of soda, right, in a hot car, it'll implode.
Or in the.
So, what? V1 all over T1 is equal to V2 all over T2 is what our equation would look like if we were to isolate everything, right? Gay-Lussac's law, okay? I think it was two guys, Gay-Lussac's, together. It was French. Okay, they determine the next law. So it is pressure and temperature when isolated also have a direct relationship, which makes sense again. If you have higher temperature, you have a higher kinetic energy, you're going to create more pressure as they collide against walls. So it becomes P1 over T1 equals P2 over T2. Okay. So this is a really handy dandy thing to have and notice, because sometimes what you'll find is the information they give you only relates to two variables changing. And you're like, oh, I don't know how to stick that in the ideal gas law. And it's like, you don't have to stick it in an ideal gas law. You stick it in a sub law that's derived off of the ideal gas law. Yes.
Did these people just like move off with the ideal gas law, or did they like?
No, they actually preceded it. They preceded it. Yeah. But last year I felt it was a little clunky, so I decided to do it this way, and I think it's better. It's kind of like, here's the big idea. Here's a way you can manipulate the equation to find the sub variables. Okay. I think it works better that way. Charlie and I agreed on that one. Charlie, by the way, has helped a lot reorder a lot of this to hopefully make it even smoother than when he learned. Okay. So although Charlie worked very hard, but also kind of naturally gifted in the topic. So he figured out a lot of things in all my mistakes. So Charlie's the real teacher here. So but if you try to take my paycheck, I will hurt you. Okay. So, okay. So now let's quickly take a moment to talk about, okay, we've talked about all this theoretical ideal situation. Oh, the gas is perfect. It moves in straight line vector motion. As you can tell, I lost my voice at Disney. Oh, all these things, blah, 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 blah. Well, here's the situation, folks. Here's the situation. Nothing is ideal, right? Don't we know that, folks? Like, a lot of you are single tomorrow, but that's okay, because one day someone will love you. So I'm just kidding. A lot of people love you. You're very loved. So anyway, what happens though when we look at actual experimental values? Okay, what happens when we look at actual? Nathan, what's on your device? Would you like to share with the rest of the class?
It was pretty cool.
It was pretty cool. Shall we share it? So with that's right, Nora. Undo. So what happens when we look at the actual data? We see variances, right? We see a discrepancy between what should be true, but what we actually get. And this is our little mini topic on comparing ideal versus real gases, which by the way is a common MCQ and portion of FRQ. Tonight's AP problem walks you through a couple like, why did we see this? And it's a differentiation between ideal versus real gas law question. So first and foremost, real gases, okay, real gases, they have volume. Okay, they have volume. Okay, there is some space to them that they take up. They also are inelastic. When they collide, they do lose some energy. They also experience IMFs. And they don't always move in straight line vector motion. Okay, so what we see is that when we have pressure, volume, and temperature be constant, so when P, V, and T are constant, we see that hold on. Why is this not right? Hold on. Are not constant. We deleted some extra things to remove it. So I just had to make sure that I'm up to date. Yes.
For the case of inelasticity, would temperature just be reintroduced back to the system as they call it?
Yeah, it levels things up a little bit. I think the real reason maybe that your kinetic energy goes down is the IMFs and interactions between the molecules attracting each other.
So the energy, the energy gets absorbed as potential. It transforms into something else, so it doesn't stay pure kinetic. That's part of the problem.
But isn't temperature itself kinetic energy?
Temperature is not itself a kinetic energy. Temperature itself is a measure of kinetic energy, but it itself is not kinetic energy, nor is it the energy of the entire system itself.
But I guess the point I'm trying to make is if you took a non-ideal gas with vacuum that had plastic conditions, and then you made it interact with itself, it's not necessarily losing anything within the system, and thus would have PV stay.
Theoretically, no, but the way it behaves is like it does. In terms of how, and the real issue with inelastic collisions is that because they're inelastic, they have more opportunity to stick and do IMFs. That's the real issue behind it. And it's actually less to do with energy and more to do with, oh, I actually kind of interact with it. I have H bonding or dipole or LDFs holding me there for a little bit longer than I should be, creating slight variance in my measured values, which at a macro scale, when blown up with moles and moles and moles of gas, can create actually quite a significant difference.
And that being held together is converting the kinetic energy to potential.
Exactly, because of the position. So when P, V, and T are not constant, I apologize. We deleted a section. When P, V, and T are not constant, okay, that would be like conditions of high pressure, the exact opposite of ideal conditions and low temps. When things are moving slower, you get more opportunity to stick to one another. Real gases in general have, okay, a either lower volume than expected, in terms of you would think that I'd fill this much space, but in reality, I don't fill that much space, okay? Lower volume than expected and lower pressure than expected. Sorry, it's a conspiracy theory. I'm working with pens to help use up more of your ink, so I gotta have you write more. So,
No, because literally the AP.
Yeah.
Problems are so much better.
So what we see then is, and I think I kind of repeated myself, is the big idea here is IMFs. That tends to be the main reason right here that we and the FRQ focuses on when talking about non-ideal gases or real gases, is that In those conditions, you get more IMFs. Okay, you're moving slower, you have more time to pass by. If you're moving at super high velocity and you run into someone, like some of you have seen me run across campus, I wave and say, hi, right? If I bump into someone, I'm mowing them over. Like it's no stopping, okay? But when I'm slower, I can create a high five, right? I can create more interaction, okay? It happens. They're in my way. So anyway, yes.
Yeah. Why don't the molecules try to resolve that pocket and that interkinetic energy? As in, like, why do IMFs mechanically create these pockets, I guess, and how do they keep that?
Create these what?
Like, how do IMFs create that?
It's more the positioning of the interaction that has a stored like nature to it. It's not about creating potential energy. It's about going through a conversion of where that energy is being expressed. So that energy is being absorbed slightly by the molecules to interact.
Wouldn't it be absorbed as temperature then?
No, temperature is not a real thing. Temperature is a measurement.
Or kinetic energy?
It would be absorbed as, well, it would come in the form of kinetic energy. It would be absorbed as kinetic energy, but then it would be transformed almost instantaneously to potential to interact in the way that it does. And then, yes, it would keep moving because you would still have an overall input of kinetic energy. I think you're getting too detailed. I don't think it's going to help you, to be honest, at all. Like, I really don't.
We should
So,
just like at seminar one time just discuss all these.
Yeah,
questions,
because
they're
they're
not very
fair.
relevant, but they're very interesting.
They're interesting, but they won't help you at all on the AP exam. So, we also know that real gases, by the way, take up space and container and they have actual volume, which I already kind of said. So I'm actually just going to exit that out because I kind of talked about it. And for warm up tomorrow, why don't you quickly prepare an answer for the next question and we'll talk about it tomorrow. And that's the end of today. Good job, guys.